Hello student, welcome to the classical mechanics course. In the last lecture we started our discussion in the center of mass system. Okay, so where we discussed the various concepts in the physics and what are the constraints on the system in order to obey the Newton's laws of motion. So this was the story of last lecture. Okay, so the conclusion from the last lecture is that if you want to solve the problem based on the Newton's laws of motion, in that case force under the consideration should be the external force, since there is no such internal forces involved while you considering the system which can be solved, which can be described with the help of Newton's laws of motion. Okay, so this was the last story. In today's lecture we will see what are the different conservation laws supposed to be obeyed when we study the Newton's laws of motion. Okay, so as we know, there are various quantities, various physical quantities which should be conserved during the motion of the charge, motion of the particle in the classical mechanics. So for the sake of completion, we'll only go on through this few of the conservation laws. And the first conservation law is the conservation of linear momentum. So we'll start with the conservation of linear momentum. So what is linear momentum basically? So the conservation of linear momentum. So before going into the details of how this conservation of linear momentum will be obeyed when we study the Newton's laws of motion. So what is the meaning of this momentum basically? So in the Newton's second law of motion we study what is momentum. So the momentum is the product of mass into velocity. So during the motion of the particle, during the motion of the any body which can be described with the help of Newton's laws of motion, so due to its velocity and mass it possesses a momentum. So how this linear momentum conserved during the motion of the particle? Let's start. So as according to Newton's second law, so as we know, what is the statement of Newton's second law? Second law. So rate of change of momentum is equal to F external. So we already see F external. This was the last topic. This was our last topic. But suppose if we consider according to Newton's first law of motion, if there is no external force acting on the system, in that case the body will remain in its state of rest or state of motion. Suppose if this F external acting on the system is 0. Suppose this F external from this suppose this equation number 1, suppose if F external force acting on the system is 0, so this dp by dt, rate of change of momentum, comes out to be 0. So this dp by dt is again 0. So derivative of some quantity when it comes out to be 0, so in that case this quantity is constant with respect to time. So what is the conclusion from this statement? So dp by dt is 0, therefore the p bar is equal to constant. Therefore during the motion of the particle, if external force acting on the system is 0, the momentum of the system, momentum of the particle during its motion is not supposed to be changed. Okay, so this was the constraint on the system while we studying the Newton's laws of motion. Therefore, if external force acting on a particle is 0, then the total momentum of the system, total linear momentum, we are strictly speaking linear momentum is conserved quantity. Okay, when linear momentum is conserved, when external force acting on the system comes out to be 0. So this is the first conservation law, we can say, conservation of linear momentum. So as we know in the 11th 12th standard physics, we know how this linear momentum is conserved when we study the different motions of the particle. In the next few module, we study these collision of the bodies. Okay, so where many of the problem which based on this conservation of linear momentum. Okay, so this is all about this conservation of linear momentum. So when the particle is moving in the straight line, we are talking in terms of the linear momentum. But suppose particle is moving around the curved path. So in that case, what are the conserved quantity which should be taken into consideration while solving the Newton's laws of motion? So the quantity which we normally discuss when the particle or the motion of the object in the curved path or a circular motion or rotational motion, we can say. So in that case, angular momentum comes into picture. So we should know what are the quantities which should be remains conserved when the particle not moving in the straight line, it is moving in the curved path. So let's look at these parts of this lecture. Okay, so the next conserved quantity is the conservation of angular momentum. So the conservation of angular momentum. Okay, so this is not the case where we study when the particle is supposed to be moving in the straight line. So in the last lecture, we study the system. We have this system, and system consists of n number of particles. So starting from m1, m2, m3, m4, mi, and up to mn. So those are the number of particles, and we consider O as a reference point, and with respect to reference point, we give the position vector according to the this initial point O, and from that we derive this whole center of mass system. Okay, so this was the last lecture. So if we consider those n particles, suppose if we consider those 1, 2, 3, 4 up to n particle, and we are assigning linear momentum to each and every particle. So the linear momentum of this first particle is P1, linear momentum of the second particle P2, third particle P3, up to n particles. So Pn be the nth particle, nth momentum of the particle n. Okay, suppose if we consider the any particle from this 1 to n particles, suppose if we consider the any particle, let's say if we consider ith particle. So if for the ith particle, if Pi be the linear momentum of ith particle. Okay, so I may be the any particle, it may be first particle, second particle, or any particle. So this is Pi be the ith momentum of this ith linear momentum of the particle. So how to represent angular momentum of the particle? So from basic kinematics, what is the relation between linear momentum and angular momentum? So the angular momentum of ith particle is, so how to represent linear momentum of ith particle is Li. So I write this with the small letter in order to represent the linear momentum of ith particle, and since it is scalar quantity, it should be represented in terms of this bar. So Li be the S from basic kinematics, Ri bar cross Pi bar. So this is the linear momentum of the ith particle. I may be the any particle from this whole system which consists of n particle. So suppose if you know the linear momentum of the ith particle, how to calculate the total angular momentum of whole system? Yes, by making a summation. So the angular momentum of angular momentum of total system is, yes, what is angular momentum of total system? So we can represent these L be the total. I'm writing this with the capital notation. So capital L be the total angular momentum of whole system. So it can be represented at summation runs from 1 to n. Since we are summing all those linear angular momentum of all those particles which consist of the system, first particle, angular momentum of first particle, second particle, that means L1 plus L2 plus L3 plus L4 up to Ln. So I am writing these L1, L2, L3 by this summation sign. So this is Li bar, which is equal to, again, summation sign as it is, I1 from n to n, Ri bar cross Pi bar. Okay, so let's say so this is equation number, this was equation number, let's say 2, this 3, this is 4, and this is equation number, let's say this is equation number 5. So therefore if you differentiate equation number 5, we'll get the change in angular momentum with respect to time. So differentiate equation 5, of course, with respect to t. So if we differentiate equation number 5 with respect to t, so what do you get? So let's look at, so dl by dt is equal to, yes, summation sign as it is. So again, so I just write d by dt of, what is L value? It is summation over I. I'm not writing for everywhere for I runs from 1 to n, so you can consider it is. So I summation over I. So Ri bar cross Pi bar. So I can easily keep it this summation sign outside the integration, outside the derivative part, since it is not depend on the t and derivative. So I can write this as summation over I d by dt of inner term, so that is Ri bar cross Pi bar. Okay, so what is the derivative of these two terms? Yes, product rule. Derivative of first term keep second term as a constant, derivative of second term keep first term as a constant. So summation sign as it is. So I just write this derivative of this first term, second term keep as a constant. So dri by dt cross, since it is cross product, so Pi plus Ri as it is, first term as it is, and since it is cross product, so dpi by dt. So this is the expansion of this term. So I'll multiply, I'm summing all those terms, so I separately summing each and every term. So I can write this as summation over I d Ri by dt cross Pi. So this is first term. Second term, summation again as it is, Ri bar cross dpi by dt. Again this is second term. Okay, so this is equation number, let's say equation number 6. This is equation number 6. So from equation in the last lecture we studied the equation for the force. So equation for the force is therefore, as we know, what do you know? So dp by dpi by dt is equal to F external. So this was the we pointed out these force acting on the system, which is the change in its momentum. Okay, so instead of this external, which is only the Fi, force acting on the system. I, what is I? since Fi bar is Fi external plus Fi internal. So it is sum of these two forces, external force and internal force. Okay, so this is equation number, let's say equation number 7. So we can use this dpi by dt in these equations. So before substituting this value, let me figure out these equation number 6. So from 6, so I'll just simplify this dri by dt term. So dri by dt can be written as, yes, so I'll simplify this term. So summation from this summation, I'll simplify this term. Okay, so keep it, watch on this term. So I as it is, so dri by dt cross pi. So what is pi? Yes, pi bar is mi vi bar. So this dri bar by dt cross mi into vi bar. Okay, so this is all about. But what is dri by dt? Rate of change of displacement vector with respect to time is nothing but the velocity vector. Since mass is not depend on the time, so I'll keep it outside this derivative part, and instead of this dri by dt, since dri by dt is vi. Okay, so instead of this I'll put the value. So summation I mi as it is, since it is constant with respect to time, so vi cross this vi. So this vi for this term and this vi as it is, so mi is outside the derivative part. And what is the cross product of self vector? It is 0, so it is comes out to be 0. So instead of this value I put the 0 value, and instead of this dpi by dt I'll put the fi value. Okay, so therefore this I'll write this dl by dt as separately. So summation over I as it is, since this ri bar cross dpi by dt. Okay, so this is all, and we have to substitute this instead of this dpi by dt with this f external. Okay, so f external can be, but what is the value of external, by the way? What is I external? If we sum up all those forces acting on the system, instead of this fi, we can write this f external as a fi, force acting on ith particle is the external force plus internal force acting on the ith particle due to rest of the particle. Okay, so this was this we already know from the last lecture. Okay, so this fi can be written as, it can be written as, I can write this as with the fi can be written as fi external plus fi internal. Okay, so plus summation prime j. So you know the why I'm written this prime. So this was the story of the last lecture. So internal. So instead of this dpi by dt I'll write this value. So how can I return this term? So dl by dt can be written as summation over I as it is, since ri cross, we have these two terms, that is fi external bar plus fi summation over j prime f ij, so internal. Okay, so this is, so separately multiply, separately take a cross product of these two vectors. So it can be written as this summation over I ri cross fi external plus this summation and this summation. So we have these two summation, so keep it as it is for a while. So we can write this equation as a so it can be written as plus summation over I as it is, summation over I as it is, and instead of these rest of the value I keep it those values as it is. Therefore the Ri bar cross summation over j prime Fij internal bar. Okay, so this is the equation, this is the we can say this is next equation 7, equation number 7. But from the equation 7, how to write the second term? Summation over I Ri cross summation over j. So I can write this term again over here. So summation over I into Ri bar as it is cross summation prime j Fij internal. So how to write this term again? So I can write this term as it is, so I as it is. So I can write this Ri over here, since this second summation is not depend on the I, so I can directly write I over here. So this summation I can write outside this bracket. So summation again j prime Ri bar cross Fij internal. So see, consider, so this Ri is depend on the ith coordinates and the second summation is depend on jth coordinates. Since it is for with respect to this j, this first quantity is constant, so instead of this putting this Ri outside this summation, I can write this inside, since there is no change in the equation. Therefore the summation over I summation over j, this Ri cross this Fij internal bar can be again written as, if I change the order of summation, there is no change in the, and there is no change in the this equation. Since instead of this I just write this j, so j summation over I prime. So instead of r I have to write this rj bar cross Fj I internal bar. Okay, so I just reverse the notation of this summation sign, since it is only changing the I and j coordinates. Okay, so this is all. So therefore how to write the next step? Therefore, so the summation I j prime, so I'll write this summation this equation with the summation ij and prime for that. So, okay, so summation over ij, so Ri bar cross Fij, and of course this is internal, we are talking about the internal forces, which can be written as, okay, so this is summation. Instead of this ij I just write this equation. Okay, so instead of this I write this ij. Okay, so don't confuse with whether how this summation or ij comes from. Okay, so it counts the, since it is running from I runs from 1 to n, j again runs from 1 to n. Okay, so I can write this as if you like this, you can ask the question. So if ij prime Ri bar cross Fij internal plus again count for the jth coordinates. Okay, again it can count for the jth also, plus Rj cross Fj I bar internal. Okay, so it counting for the second, but while this counting for the second time, it may be count Ri Fij plus Fji, it is again same, so those forces are same, so it again calculating this in 2 times. Okay, so Rij Rji, it is again same. So in order to avoid this ambiguity, I just multiply this with half. Okay, why I am multiplying this half? Because it count twice this quantity. Okay, so in order to delete, since Fij Fji 2 times, so in order to cancel these 2, I just write this multiply. Okay, 2. Okay, 2. Okay, so this is all set. So summation as it is I j prime. So by the way, what is Fij and Fji? Yes. So I just write this, and then I'll explain you why I'm writing this Fij internal plus Rj again as it is. What is, by the way, what is Fji? Fji with the internal force acting on jth particle due to ith particle. It is again same, the force acting on ith particle due to jth particle, but equal in magnitude but opposite in the direction. So instead of this ji, can I write this minus Fij internal? Yes, of course I can write, since according to third law, of course Newton's third law, Fij internal is equal to minus sign for it is in the opposite direction to Fij, is equal to Fji internal. So according to Newton, action reaction forces, so those forces are action reaction forces. Okay, so instead of this Fji, I'll just put the minus Fij. So I'll write this equation again as it is. So half summation over Ij prime. So Fij common, keep it outside. So before Ri, okay, Ri, and over here this Rj, so minus sign as it is, so minus Rj cross Fij. Okay, so this is the equation. But what is Rij from last equation? But Ri minus Rj is again Rij. Distance or the position vector between point I and point j. Okay, so this is, so instead of Rij, suppose instead of this Rij, suppose if I put the value Ri minus Rj, so I can write this equation as, so since we are writing this equation, so summation Ij prime Ri bar cross Fij internal is equal to, so half as it is, so half summation over Ij prime, instead of Ri minus Rj, I write Rij bar cross Fij bar. Okay, so look at Ij. So what is the direction of this Fij, force acting on ith particle due to jth particle, and since the forces are internal. Okay, so don't confuse with the notation. Okay, so internal forces. Okay, so what is the direction of this Fij and Rij? Since those two vectors, position vector Rij and force acting on the ith particle due to jth particle, are in the same direction. Okay, since Rij and Fij internal acting along the same direction. So if two vectors are in the same direction, the angle between these two vectors is 0, so cross product of these two vectors comes out to be 0. Therefore I can write this Fij prime Ri bar cross Fij bar internal S comes out to be 0. So this is equation number, I think it is equation number 7 or 8 or 9, equation number 9. Okay, so how to write this complete equation? So our original equation for dl by dt is again, so dl bar by dt is equal to, so only one term is remaining, so this term is regarding the external forces. So Fi is Ri bar cross Fi external bar. Ri be the position vector of ith particle and Fi be the external force acting on the ith particle. So R cross F, what is this? It is torque acting on the system. Since force is external, so this quantity can be represented as external torque acting on the system. So this is the summation over I. I can write this as a Ni. What is Ni? Ni be the external torque acting on the ith particle. And if you sum up all those torque acting on the system, I'll get this total N. Okay. So dl by dt is equal to external torque acting on the system. So there is no such big deal. We already know this equation from the basic physics. The N, that is external torque acting on the system, is equal to summation over Ri cross Fi external force. Okay, since this is a sum up over ith particle, so therefore this is total torque acting on the system. This is total torque acting on the system. Okay, so suppose if N external is equal to 0, so if there is no torque acting on the system, so in that case, how to write our original equation? dl by dt, it is 0. So external torque acting on the 0, therefore the rate of change of angular momentum is again 0. Therefore this L is constant. Derivative of certain quantity is constant, so L is again constant. So what is the significance of this equation? Let's say 10. So what is the meaning of this equation number 10? If external torque acting on the system is 0, in that case angular momentum of the system is constant in nature. That means if there is no external torque acting on the system, initial angular momentum is equal to final angular momentum. Therefore, if external torque acting on the system is 0, in that case the total angular momentum of the system is conserved. Okay, so at the end I will summarize the what is the agenda, what was the agenda of today's lecture and what we learned in this lecture. So we started our discussion by making a certain constraint on the system. So what are the different laws supposed to be obeyed when we consider the Newton's laws of motion? In first case we discussed the linear momentum of the system. So in that case, if external force acting on the system comes out to be 0, in that case linear momentum is conserved. Okay, so while discussing the linear momentum, we worried about the what happen if in case of the particle moving in the curved path. So when particle moving in the curved path, it possesses the angular momentum, it possesses the angular motion. So when we are talking about the angular momentum of the particle, so while discussing all those forces acting on the system, that is the internal forces and external forces acting on the system, so after the discussion, after the thoroughly gone through this mathematical calculation, we came to know that while considering the angular momentum, we only deal with the external forces, external torque acting on the system. Since change in the angular momentum comes out to be the external torque acting on the system. So when the external torque acting on the system comes out to be 0, in that case the angular momentum of the whole system is conserved. That means initial angular momentum and the final angular momentum is constant. So this was the story of today's lecture. So in the next lecture we'll again see what about the energy, whether energy is conserved while considering the Newton's laws of motion or it is not conserved. Okay, so this will be the next topic. So for today, I'll stop here. Thank you very much.